Welcome back and congratulations for finishing the introductory module for this course. We're going to move on now and get into looking at volume control modes of ventilation. There are two tutorials here. The first one's going to look at volume assist control and the second one looking at synchronized intermittent mandatory ventilation. I hope you enjoy these tutorials and I guarantee you'll learn something. This is tutorial 5. We're going to talk about volume control modes. And the first mode I'm going to talk about is probably the most popular worldwide volume control mode that's used in the ICU, and that's volume assist control. Previously in this course, we did 4 tutorials on setting up a mechanical ventilator. The first tutorial was on the control of ventilation, and this is essentially the 2 different platforms on which conventional ventilation is built. On volume control, where you have volume targeted ventilation with pressure variable, pressure control, which is pressure targeted and volume variable, and a modification of that, which is known as volume guaranteed pressure control. We looked at the flow patterns, the sinusoidal flow pattern of spontaneous breathing, the constant flow pattern of volume control, and the characteristic decelerating flow pattern of pressure control. We looked at triggering, how the ventilator knows it's time to give a breath. And we found that this was achieved usually by time triggering, but there's also negative pressure triggering and flow-by. And flow-by triggering is now the standard mode of the patient interacting initially with the ventilator. Finally, we looked at cycling, how the ventilator knows it's time to go to expiration. This can be achieved, and it usually is in control modes, by time cycling, but the ventilator can also volume cycle or pressure cycle, and in specific situations such as pressure support, the ventilator can flow cycle. In this tutorial, we're going to move on to look at the different modes of ventilation, what happens when the patient comes in and you want to start them on the ventilator. And we're going to look initially at volume control modes, and then we'll move on to pressure control. And in this particular tutorial, I'm going to focus on volume assist control. Now, who might you decide you might want to use a volume control mode of ventilation? Well, this is the type of patient that I would suggest you think about. Leonard is a random patient who was admitted to the ICU and he has normal lungs, but he's intubated and he's paralyzed. He's had a neuromuscular blocking agent. And perhaps he's come from the operating room, perhaps he's come from the emergency room. For example, he may have taken an overdose or he may have had a brain injury. So he's got normal lungs, but he's not able to breathe. What mode should we use? When we think about the vent modes, we really have only 3 things we have to start off with. Volume control, pressure control, and dual control, which is volume guaranteed pressure control. I want to make a point here and now that despite what you might hear from loud-mouthed, opinionated people, there is no ventilator mode that's better than any other. The quality of mechanical ventilation, the precision, the skill depends on the operator. And all the modes that I'm going to discuss can be used by anybody, and they will work really well in your ICU if you're careful and you know what you're doing. In this series of tutorials, I'm going to use this jerry-rigged model of a ventilator to describe the different modes and how they operate. If you look over on the right-hand side of the screen, you'll see this is where the gas goes into the ventilator. I have a series of controls here called the vent controls, a timer device, because remember, controlled ventilation is usually time triggered. We have a nice waveform display that will show us flow and pressure. We have a bellows. This could be a piston. This will drive gas into the patient. We have a gas outlet and an inspiratory flow sensor, inflow tubing, an airway device, in this case an endotracheal tube. It could be a face mask, it could be a tracheostomy. These are the patient's lungs, and this is the patient's diaphragm. We now go to the expiratory limb, so we have our expiratory tubing, our expiratory flow sensor, and finally our exhaust device for removing gas or scavenging gas from the system. So that's the setup we will have in the subsequent parts of this tutorial. Let's just look at an overview of why one would want to use a volume control mode. The major advantage of volume control modes of ventilation is pure ease of use in a patient who is not interacting with the machine. When I say not interacting with the machine is that they're not synchronizing. You don't require the ventilator to interact with the patient and make sure that the breath that they take is synchronized with the machine breath. And you can be confident on these modes that the patient will receive the desired minute ventilation to ensure both oxygenation, as evidenced by the PaO2 or the oxygen saturation, and ventilation, which is evidenced by the pH and the PaCO2, are within the range that you desire. It's neither helpful, though, or desirable to keep someone like Leonard paralyzed in the ICU. It's fine if he's in the operating room, but there are very, very few indications for continuing to use neuromuscular blocking agents in the ICU. Really, in this day and age, it's profound hypoxic respiratory failure or perhaps tetanus. But for most people, you have to turn these drugs down to let the diaphragm move, because the diaphragm almost wants to be moving and it becomes dysfunctional if it doesn't. So you have to be mindful that even if you put Leonard on a mode of ventilation that's purely just giving him volume all the time, that at some stage he will want to interact with that ventilator in the next hour or two. And that's why there has to be some form of ventilatory assistance in an ICU ventilator. If we're going to use volume control ventilation, we need to know the setup, and the important components of the setup are as follows. Firstly, you set the number of breaths, usually between 10 and 15 breaths per minute, and then you set the desired tidal volume. Because it's volume control, you need to set the desired tidal volume. As a rule of thumb, for your average height woman, roughly 350 mils will work by not giving them excessive tidal volume or too small. For the average height man, 420 mils is the ballpark. Obviously, if they're very tall, if someone is 2 meters tall, they need 550 mils. But rarely would a woman need more than 400 mils and a man more than 500 mils. And be aware, of course, that the tidal volume, even though if you read the journals, it will say mils per kilo, but it's really mils per kilo of predicted body weight based on height. It's all about height. The taller you are, the bigger your lungs are. Obviously, if you put on weight and become obese, your lungs don't get any bigger. So it's all about the height. So that's a kind of a ballpark figure. Then you set the inspired oxygen tension, usually between 30 and 50%, depending on the saturation and the PaO2 goal. You apply PEEP, 5 centimeters of water being conventional, but you can go up on this depending on the body habitus and the degree of atelectasis. Again, obesity, you might need a little bit higher PEEP. You set the peak inspiratory flow of 50 liters or so per minute. That's the V max. Decide whether you think an inspiratory pause is needed. That gives you a longer inspiration. Sometimes you'll just set an inspiratory time on ventilators. There are a whole group of ventilators out there that you don't set the peak flow and you just set an inspiratory time, and the flow will be generated over that time. But it's conventional if you want a pause in volume control ventilation, if you want a longer breath to improve oxygenation, to set an inspiratory pause. And finally, decide that on what type of trigger mechanism to use, whether it's negative pressure triggering or flow by triggering, for when the patient inevitably starts to breathe. In this day and age, it is conventional to use flow by triggering, as I discussed in tutorial number 2. Let's start with volume assist control ventilation. This is possibly the most popular control mode of ventilation in the world. It has a lot going for it, and I'm going to spend a little bit of time teasing through what actually goes on in volume assist control. Let's start with inspiration. You'll note here that on this particular patient, the settings are volume assist control, and I have set a tidal volume of 450 mils, a rate of 12 breaths per minute, and a peak flow of 50 liters. The control breath is triggered by time. So it time cycles, and when that happens, the breath is delivered. And you can follow the animation as the breath goes into the patient. Gas passes from the inspiratory tubing, and in this case, it goes all the way into the endotracheal tube and into the lungs. The lungs inflate, and the diaphragm and chest wall move down and outwards. In this situation, the chest wall, the lungs, and the diaphragm are passive. They're being pushed out. They're not moving themselves. And so the thoracic pump itself is a passive observer in all of this. And part of the role of the breath is to move all this tissue out of the way. On the ventilator, the breath will register as a controlled breath. For example, if you look carefully in that, where I've drawn that red box, there's a little C there on the left-hand side on the smaller screen indicating a controlled breath. At the end of inspiration, an inspiratory hold can be applied if we are time cycling inspiration, or if we're not, the ventilator will immediately cycle to expiration. On the waveform screen, you can note the square-shaped waveform for constant flow and what I call the shark's fin pressure waveform for volume cycling. Moving on to expiration. So here are our inflated lungs. The bellows is downward, end inspiration. Expiration starts when either the volume has gone in, volume cycling, or else after the pause, the expiratory valves open and gas flows along the pressure gradient from high pressure in the lungs down to low pressure on the expiratory limb, and that pressure, it stops at PEEP at the positive end expiratory pressure level, or ZEEP or zero PEEP if you haven't applied it. And here is the gas flowing through the system. You can see that during expiration, the bellows refills. Sometimes when we come to IMV, you'll see there's a bag that refills during this. On the pressure waveform, you will the flow waveform, you will notice the expiratory flow pattern, which is the same as you'll see in all of these waveforms. It's that elastic recoil flow. Above that, you will note another number, that is the exhale tidal volume. And this is the most important number that's delivered. This is the number that the volume that represents the volume that comes out of the patient's lungs. It's what the patient exhales. So we have two different numbers for tidal volume: the inspired tidal volume, which is what the ventilator delivers, and the expired tidal volume, what the expiratory sensors recognize coming out of the patient. These should correlate. If they don't, there is a leak somewhere in the system. This may be caused, for example, by a piece of tubing that's partially disconnected, or a hole in the tubing, or else there's an issue with the endotracheal tube. For example, there may be no cuff, the cuff may be ruptured, or else the cuff may be sitting above the vocal cords in the larynx, and gas is escaping around the cuff into the mouth and out into the atmosphere and not going back into the expiratory apparatus. So when you've started someone on volume and controlled ventilation, you need to make sure that those numbers are correlating within about 10%. Now let's move on to assisted inspiration. If you look at the little switch there underneath the bellows, you can see that I've set flow triggering. That's that V with a dot above it. We could also do negative pressure triggering. And the patient at some stage will start to participate in mechanical ventilation, unless, of course, they're paralyzed with neuromuscular blockers or high-dose sedation with opioids. Otherwise, the diaphragm itself will start to move and the patient will desire taking a breath. So that whole thoracic pump will start to move. So let's roll the animation to see what happens when the patient starts to trigger a breath. First of all, you can see we have our flow by going on, flowing around the circuit. And eventually the patient takes a breath and flow goes into the lungs. It's recognized by the flow sensors on the expiratory side that the patient has deflected the flow, and the ventilator has triggered now and generated a flow of gas into the lungs. And in this situation, the patient will have been given a tidal volume 450 mils. If you look at the waveform, we're seeing a constant flow waveform. It's a volume controlled breath, a volume assisted breath. It's a volume breath. There's a little divot before the pressure waveform and then a shark's fin picture. So this is a volume assisted breath that volume cycles. You will also note, if you look carefully at the little screen underneath the main screen, that instead of the C that was present on our previous picture, there's an A telling us that this is an assisted breath, not a controlled breath. Again, expiration is an entirely passive thing, and it is identical for an assisted breath versus a controlled breath. But here's the most important thing about volume controlled ventilation. If you're on volume controlled ventilation where it's assist control or any other mode, the tidal volumes are identical on the controlled breaths versus the assisted breaths. The machine will only deliver the tidal volume that you have dialed up. The rate of flow can be adjusted, but the tidal volume is the same. This is the screen setup for volume assist control. We can identify the volume control here. We identify the mode of ventilation up here. This is assist control. The next thing we set up is the rate, in this case 15. The tidal volume, in this case 420 mils. They're the really basic settings that you will do in any ventilator with volume control. To this we add in the inspired oxygen tension. In this case, this patient is modestly hypoxemic, so they're on 45% oxygen or an FiO2 of 0.45. Allied with this is a PEEP of 7, which is an entirely appropriate PEEP, and we'll talk about this later in the course for that level of oxygen therapy. We've also set a peak flow, and the peak flow here is 40 liters per minute. We've set an inspiratory time, so this will be a time cycled breath, not a volume cycled breath. And the plateau time, that's the inspiratory hold, is 1 second. That is quite a long inspiratory hold. We set a flow pattern, in this case a square flow pattern. And finally, one thing that's really important if you're setting a patient up on volume controlled ventilation is to be really careful about the airway pressures. Why would you do this? Well, first of all, you can do something really stupid like put a 4-year-old child on a ventilator and give them a 500 ml tidal volume, which is massively excessive and could destroy the patient's lungs. So by having a pressure pop-off level, it means that with this entirely inappropriate tidal volume, once an airway pressure is hit, for example, here at 40, the pressure is just released from the machine, and hopefully the person who set it up will get the message that they've made a terrible error. But also there are times when the patient will start coughing, and coughs generate a lot of pressure within the airway, and you want that to be cycled off. You don't want that cough being stacked up on top of a tidal volume because it can cause a lot of stretch injury to the patient's lungs. So you must always put in a peak pressure limit on the ventilator. Now this can be problematic. I'll get back to this a little bit later on, but you must set it, and it has to be a realistic pop-off level. Don't do something convenient for yourself like setting this at 50 or 60 or 70 centimeters of water. Here it's been set at 40. That's quite generous, but it's because this patient is presumably a little bit hypoxemic. A lower level of 30 might be more appropriate for the majority of patients, but just be very careful. This is a very, very, very important thing to set on a patient who is on volume controlled ventilation. Have a look at these flow and pressure waveforms. And think about this for a second. What is the first thing that strikes you about these waveforms? And then the second thing that strikes you? And then the third. So pause the video for a moment. Just look at the waveforms and the data that's in front of you and tell me how much you've learned from the first 4 tutorials. The first thing that I notice if I look at this is the square-shaped waveform here. You can see the flow waveform. This is a constant flow waveform. So instantaneously, I know this must be volume controlled ventilation, and the peak flow is there somewhere between 50 and 60 liters per minute. The second thing I look at is the shape of the pressure waveform, and it looks a little bit, in my view, like a shark's fin. See that there? That's a shark's fin. And I think that waveform looks a little bit like a shark's fin, so I call that the shark's fin waveform. So this is volume control and volume cycled breath, right? So the breath ends as soon as the peak pressure is reached. So the volume goes in and then it immediately cycles to expiration. And you'll see that there is no inspiratory hold between the end of inspiration, that's the end of the blue line on the flow waveform, and the beginning of the red line. The two brownish lines are just interconnectors because it's on the same screen. Finally, you'll notice a little negative deflection here on the pressure waveform. It's relatively negative with respect to PEEP. I call this a divot. I don't know why, it just kind of reminds me of a golf divot, where this little divot occurs just before the pressure waveform. So a little bit negative, then you get this upward deflection of the waveform. This indicates that just before the breath starts, the patient is generating negative pressure within the airway. And this, because a breath immediately follows this negative deflection, the patient is triggering the breath. But the breath that follows is a volume-controlled, volume-cycled breath, hence the shark's fin. And the breath that follows this one is identical to this breath, the first breath that we're looking at. So the first breath is an assisted breath, it's a volume-assisted breath. The second breath and the third breath, where there's no divots, are volume-controlled breaths. Importantly, looking at the tidal volumes, you can see that all of the tidal volumes are identical, whether the patient has volume assisted or volume controlled. Identical tidal volumes here at 475 mils. So this is a classic picture of volume assist control. On this screen capture, you can see that the patient is on volume assist control with a tidal volume of 470 mils and a modest peak flow of 38 litres, and a constant or square flow pattern, and a shark's fin shaped pressure waveform. Take note that the expired tidal volume up there at the top of the screen is identical to the inspired tidal volume on the bottom of the screen. Here are another series of waveforms. These are flow and pressure waveforms. Take a moment to ponder the waveforms, pause the video, and work out what's going on with this particular patient. Well, again, you can see that this is constant flow, so it's volume controlled, but there is a gap here. You can see that little gap there between the inspiratory part of the flow waveform and the expiratory part. So between the blue flat line and the squiggly red line, there is a gap between one ending and one starting. That means there must be an inspiratory pause or inspiratory hold. As a result, the pressure waveform looks a bit different. This is no shark's fin. In my view, and this is just my view, it looks a little bit like a top hat with a blip at the top of the waveform that falls down to a ledge. So this is the picture I think of when I see that waveform. The blip at the top represents the peak pressure. That's the pressure within the airways. And the flat top bit is the plateau pressure, and that's the pressure that's seen by the alveoli. So this is volume assist controlled ventilation, because you can see the little divot before the first breath, with an inspiratory pause. Just to revisit a couple of things here, we're going to just talk about triggering here. Here we have an unassisted volume controlled breath with an inspiratory pause, but there's no assistance here. So when you see this, you know that this must be time triggered. The other thing that's worth a thought on this particular case, you can see here, this looks very like the picture I showed you a few minutes ago. This patient is on volume assist controlled ventilation. There's an inspiratory pause, it's constant flow. And on the pressure waveform, you can see that I've drawn a little red line along the bottom. Both of the breaths that are delivered here have a little negative pressure divot just before the upward deflection of the pressure waveform. And that divot goes down below the red line. And that red line is the negative pressure level below which one must get to before the ventilator will pressure trigger. So this is pressure triggered ventilation. This isn't flow by triggering, and that is how the patient will trigger a negative pressure breath. You don't see that often, but it's something to keep in the back of your mind. It's something that you could consider putting a patient on if, for example, they're over triggering. Let's look at the advantages and the disadvantages of using volume assist controlled ventilation. The big advantage of volume assist control is that the tidal volumes are always the same regardless of whether or not the patient triggers the breath. The tidal volume is locked in. Now this is inherently safe because it's known that large tidal volumes of more than 6 mL per kilo of predicted body weight are associated with worse outcomes in certain circumstances, in particular ARDS. It's also important to know that the minute ventilation is locked in, thus guaranteeing that you can control the PCO2, for example, in someone with a brain injury so that the CO2 doesn't climb too high and cause intracranial vasodilatation and a rise in the intracranial pressure, which is problematic, obviously. Now, the major disadvantages, well, there's a lot of them. The first one is that there's no biological variability. This may be just a theoretical thing, but your body does not take the same tidal volume really ever. Every breath is different. Some are big, some are small, and that's part of how we function. And one wonders if you were to get the same tidal volume over and over and over again, would it cause problems in other parts of the body? Would it disrupt some of the biological oscillators that we have that run other functions in the body? So that's a theoretical problem. The second problem is that there is no weaning in this mode. It's all or nothing. So either the patient is fully ventilated or they're hyperventilating. There is nothing in between. And you can reduce the number of control breaths, but once the patient starts to breathe up, they'll just keep on getting the same tidal volume regardless of the number of breaths, and they could take 30 breaths per minute at 500 mils, which will deliver a minute ventilation of 15 liters, which is pretty much excessive for the vast majority of patients. The next issue is that the peak flow is limited. And so if a patient starts to breathe spontaneously, if they start to demand a flow from the machine that's higher than the machine is delivering, they may develop patient flow dys-synchrony. Finally, if you have a patient who has a brain injury and they start to hyperventilate, the patient will develop a respiratory alkalosis. There'll be a fall in the hydrogen ion content of blood and a fall in the PCO2. This can cause intense intracranial vasoconstriction, and this is a really bad thing in a brain injured patient. So you have to be a little bit careful with somebody who's waking up and starts to breathe up a lot. And finally, the short inspiratory times, particularly in patients who are volume cycling the ventilator, may have problems with oxygenation because the volume just goes along the path of least resistance. The machine, the ventilator, doesn't care where the gas goes. It just shoves that gas into the lungs and it comes straight back out again. There's no system when you do volume cycle ventilation for trying to make the gas go into lung units with long time constants. That can be achieved with inspiratory holds, but it's tricky enough to get right. And so it's not the best mode of ventilation if you're trying to control mean airway pressures to improve overall oxygenation. This, in my view, is the most common and most kind of irritating problem with volume assist control, and I do see it with inexperienced users quite a lot. You have a patient set with a tidal volume of 450 mils, the peak flow is 60 liters per minute, and the inspiratory time is 1 second. So it's all set up, it's connected to the patient, and next thing, this happens. you hear the ventilator goes chugga, 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 chugga. The alarm starts honking as if there was an air raid, and everybody starts to freak out. And people start pushing buttons on the ventilator. Often 2 or 3 people arrive on the scene and start fiddling with it and flipping around modes and doing all kinds of crazy stuff. It gets worse if any of the doctors start doing this because they're usually clueless about what they're doing. And eventually someone changes the mode of ventilation and it all settles down and they all go, well, we're never using that mode again because it's kind of scary what happened. And what really happened here is that the patient is pressure cycling. And when it pressure cycles, you can see here that the tidal volume is miserable. You've set up a tidal volume of 450 mils. The patient isn't even getting 250 mils. And the reason why the ventilator is pressure cycling is that 60 liters of flow in 1 second is too much for the patient's airways. The patient may have bronchospasm, they may have a lot of crud or mucus in their airways may have chronic inflammatory changes, and that rate of flow is just too much. So the peak pressure that's seen by the ventilator in those airways that bounces back on the ventilator, just it pops off and the patient hits that pressure limit that I mentioned earlier on. So it just pops off at far too early a stage before the tidal volume has been delivered. And so you end up with these really low tidal volumes and lots of alarms and a lot of discomfort for both the staff and the patient. What you need to do in this situation is you need to stop the ventilator from pressure cycling by reducing the peak flow and slowing the rate of which the gas goes into the patient. You'll most commonly see this in a patient who's actually paralyzed, who's just arrived in the ICU. So you can slow that peak flow right down because the patient is not going to run into a lot of trouble with slow initial flow. You slow the peak flow down. And in this situation now, what we've done here is we have slowed the peak flow down to 30 liters per minute, and we've lengthened the inspiratory time to 1.5 seconds by putting in an inspiratory hold. So we're now no longer volume cycling the ventilator, we are time cycling the ventilator. And here you can see that the volume goal has been achieved. The other major problem that you may encounter is demonstrated in this picture. What's wrong here? Well, you can see that this is volume assist control ventilation, and you'll note that there are 2 anomalies with the pressure waveform. The first is that the negative pressure deflection, the divot, goes almost down to atmospheric pressure during the triggering part of the breath. So the patient is taking a huge negative breath. And just that's the negative pressure you're seeing within the airway, but that it does not show you the whole picture because the transpulmonary pressure, that's the negative pressure that's within the pleura with respect to the airways, may be really, really negative. So this patient is taking a massive breath, really struggling to breathe. And then it triggers the breath. And then once the breath is delivered, the pressure waveform starts to rise and then it sags down again, like it droops towards baseline before rising up again. So you can see here that pressure waveform should look at the very least like a shark's fin or maybe even a top hat. But what you see here is it's all being scooped out. And this is a well-known problem known as demand flow dys-synchrony. The patient is demanding more flow than the ventilator is set up to deliver. The patient is gasping for breath. Now, the peak flow you can see here is set at 40 liters per minute. And we need to give this patient more flow than they're currently getting. And this can be achieved in either one of 2 ways. The first thing you might choose to do is turn up the peak flow up to 60 liters per minute so that you might match the patient's demands. But when you see this picture, you have to wonder, why is the patient on an assist control mode of ventilation at all? Perhaps this patient might be better off on a pressure limited mode where flow is unlimited, or including pressure support, or perhaps even on a T-piece. Perhaps this patient's respiratory apparatus is so strong that they're telling you it's time to come off the ventilator. Not always, sometimes patients may have this degree of dys-synchrony and be really, really hypoxemic. And so you do need to work around this. But I would argue that, aside from going up on the peak flow, you should consider going to a pressure limited mode of ventilation. This particular scenario was resolved by increasing the peak flow. This is a picture from a ventilator of someone who has demand flow dys-synchrony, and you can see how the breath is being scooped out of the pressure waveform. In this situation, the patient's on a fairly generous peak flow of 60 liters with a decelerating flow ramp. Here are a few screenshots. Pause the video on each one and see if you can describe the mode of ventilation, the flow pattern, the pressure waveform, etc. Even, is the patient triggering the ventilator? So what do you think? Well, this is volume assist control, although you don't know for sure because all you're seeing here is controlled breaths, but it's definitely volume control because of the constant flow waveform. There's an inspiratory pause, there's a peak and plateau pressure, and the tidal volumes are locked in. They're all exactly the same. So volume assist control, constant flow pattern, inspiratory pause. What about this one? Pause the video for a moment, have a look at this, tell me what you think. Well, in this situation, you need to spend a little bit of time considering this because you might think that this is pressure control based on the flat-topped pressure waveform, the decelerating flow waveform, and how everything kind of looks the same. But in fact, this is also volume assist control with a decelerating flow pattern, and it has a peak flow of about 50 to 60 liters. It's not time cycled. The real giveaway here is that the flow waveform goes straight to expiration at the end of inspiration. So this is volume cycled, and also all of those tidal volumes are identical. That's a tricky one. So that's volume assist control with the decelerating flow pattern that is volume cycled. Finally, what about this one? Pause the video for a moment, consider what you're looking at, and then follow on with me. Well, this is also volume assist control ventilation. And you can see here that the difference between this scenario and the previous one is that the flow pattern goes down to baseline and it's held there for a short period of time before it's released into expiration. So this is time cycled, decelerating flow, volume control ventilation. The patient isn't assisting any of these breaths. So this is volume control as well, even though it looks remarkably like pressure control. In this tutorial, we started off looking at volume control modes of ventilation, and I mentioned initially the principal concepts behind volume control. We discussed volume assist control ventilation and how it works and how it operates, and then we looked at the advantages and disadvantages and complications associated with volume control ventilation and how to troubleshoot those problems in the assist control mode. Next time I will move on to talk about the other commonly used version of volume control that's based on a slightly different platform, and that's intermittent mandatory ventilation, and the modern version of that, synchronized intermittent mandatory ventilation. Please join me, and I guarantee you'll learn something new. Well, that's the end of this particular tutorial. I hope you learned something. Please join me again, and don't forget to hit subscribe if you're watching this on YouTube.